Hey everyone, welcome back, and today let's solve Leetcode problem 52 titled N Queens 2. So the N Queens puzzle is a problem of placing N queens on an N by N chessboard such that no two queens attack each other. So we're given an integer n, and we have to return the number of distinct solutions to the N Queens puzzle. So in example 1, we have n to be an integer value of 4, basically meaning that our chessboard is basically going to have dimensions of 4 by 4 or an area of 16 with 16 different cells, and we'd output 2 because there are two distinct solutions to the 4 queens puzzle as shown. And the reason why we're going to have 4 queens in this puzzle is because n equals 4, and we basically have to have 4 queens positioned in a way such that no queen can attack each other, right? That's basically how the puzzle is defined to be on the first line of constraint here in the problem statement. So that's the reason why we'd output 2, and the way that's actually set up is shown right above here in these two images, right? And of course, in example 2, when n is equal to 1, we only have one distinct solution for one queen, not to hit another queen in only one possible cell of a chessboard of area 1, and so we'd only output one solution, right? So I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so ultimately, to solve this problem efficiently, we'll use backtracking, a very common technique for solving problems incrementally by building a solution piece by piece and abandoning the partial solutions when we actually realize that they can't lead to a valid solution. So to better explain the algorithm, essentially, the algorithm places queens row by row, and for each row, we try to place a queen in every column while checking if the placement is valid. For example, if it's not attacked by another queen, right? And if valid, we'll move to the next row, and if invalid, we'll basically try another column in the same row. And once we actually finish the last row, we'll increment the solution count. So for the variables or data structures to use in this problem, we'll have, of course, a count, basically a variable to keep track of the number of valid solutions. We'll have columns, basically a set to keep track of the columns that already have queens. We'll have diagonals, basically a set to track the diagonals that are under attack. For example, the difference between the row and the column, or r minus c, which we'll get into later on in the code. And we'll have anti-diagonals, which are going to be a set to track the anti-diagonals that are under attack, or basically the sum of the row and column, r plus c, right? Which again we'll get into later on in the code, right? So with that out of the way, let's just go ahead and dive straight into the code, right? So first, let's just basically define our helper or backtracking function. So I'm just gonna use the name backtracking for my function name. And for my parameters, I'm gonna have, of course, a row. I'll just type in that to be an integer. I'll have column, type in that to be a set. And all of you guys who use statically typed languages, you guys are probably dancing right now to see me type hinting in a dynamic language, right? But anyways, we'll have columns to be a set. We'll have diagonals to be, in fact, I think, a set. And we'll have anti-diagonals, like we talked about before, to be a set as well. And I'm actually just going to type in that to be, or have a return value rather of int, right? In C++, it's probably just like int main, or it is int main, not probably. I'll have like parameters int row, and so on and so forth, right? Where basically int is going to be my return type, where I have to statically define the return type before I actually define the function name or pass in the variable, the function's parameters, right? I have to actually define it using the data type or the return type of the function. Right? That's basically how statically typed languages work. It's the same as Java as well. But anyways, once I do that, now I actually have to, or actually I'll explain this code first. Essentially, we'll basically define an inner function or an inner helper function, backtrack, that performs the backtracking. And for the 4 arguments or parameters, it's going to have a row, which is the current row being considered for placing a queen. We'll have columns, which is a set of columns where queens are already placed. We'll have diagonals, which is a set of diagonals that are under attack, and we'll have anti-diagonals, which is a set of anti-diagonals that are under attack, and that will basically return the number of valid solutions found, hence why we type in this to have a return type of an integer, right, the number of solutions found, okay? Once we do this, we'll have our base case where if the row actually hits the value of n, basically meaning that we're on the last row, we can return 1. right? Again, this basically checks if we've placed queens in all n rows, and if so, it means we found a valid solution, and so we can return 1 to count this solution. Okay? And after we actually exit that base case for this backtracking function, then we'll actually initialize our solution to, of course, be 0, because we haven't actually found any solutions yet, right? And we'll loop through every column in the range up till n, right? From 0 to n exclusive, right? Again, what this does is it's going to initialize the variable solutions to 0, which will accumulate the number of valid solutions found from this point onward. And the for loop basically iterates through each column in the current row, basically trying to place a queen in each column. Okay? And essentially we'll initialize our current diagonal. Okay, I'm not sure if this is how you spell diagonal. I'm horrible at spelling. I'm gonna assume that that's right. And that's going to be row minus column. And I'll have my current anti-diagonal also to be row plus column, like we talked about before. So again, for each column, we'll calculate the current diagonal of row minus col and the anti-diagonal of row plus col to track queen attacks in both directions, right? And again, we basically have to have our base case or our checker after we initialize these two variables. So again, we'll have to basically have if the column in this current iteration, or basically our iterator on line 7, if that's actually in the number of columns, or the current diagonal is already in the diagonals set, or the current anti-diagonal is already in our basically anti-diagonal set, right? And basically anti-diagonals, diagonals, and columns are already predefined parameters or sets in our backtracking function as arguments itself, then we can simply continue, right? And in Python, the continue keyword is basically just a keyword to actually just move on to the next iteration of for loops, right? Basically, we don't want to do anything in that iteration, right? So again, it basically checks if placing a queen in the current column is valid, and if, of course, the column is already occupied, or if the diagonal or anti-diagonal is under attack, we'll skip this column with the continue and move on to the next one, right? Right, that's basically our base case somewhat, and on line 10. And if of course we don't actually fall into that conditional, we'll actually add to our column. So we'll say columns.add. I think add is the right appending keyword for sets in Python. So we'll say columns.add column. Then we'll say, okay, diagonals dot add the current diagonal in this iteration. And finally, we'll say anti-diagonals dot add the current anti-diagonal value. Okay, so again, what this does is if the position is valid, we'll add the current column, diagonal, and anti-diagonal to their respective sets to mark them as occupied or under attack, right? And actually, I think, oh my god, I literally typed that value. It's not necessary, it's just current anti-diagonal. Sorry about that. But anyways, yeah, it basically marks or adds these current values to their respective sets to mark them as occupied or under attack, right? And after we actually add these values to the corresponding sets, we'll add to our solutions, basically the number of solutions we have, plus equals in Python, and really any other main language like C++, C, or Java, or even JavaScript. We'll call it backtrack. And for our parameters, we'll add one to the row. Of course, our diagonals. In fact, I should have columns here. Okay, let me actually just redo this. Sorry about that, guys. Okay, so when we actually recursively call this backtracking function and add that return value to the solutions, we'll actually have row plus 1. We'll have columns to be the same. We'll have diagonals to be the same, and of course we'll have anti-diagonals to be the same because we've already added those values to those corresponding sets. Diagonals on lines 12 through 14, right? It's current diagonals. Okay. And essentially what this does is basically after placing the queen in the current column, we'll recursively call that backtrack function for the next row. And the result of this recursive call, basically the number of solutions from subsequent rows, is added to the solutions variable, right? Hence, what the return value is what we add to the number of solutions variable. Okay? And once we do that, now we're free to remove, or columns.remove, the current column in this iteration. And we can also do the same thing for the diagonals and anti-diagonals. Diagonals.remove the current diagonal, and finally anti-diagonals.remove the current anti-diagonal. Okay? So what this does is basically, after exploring the current column, we can remove the current column, diagonal, and anti-diagonal from their respective sets. And this basically backtracks this decision and allows us to try placing queens in other columns, similar to the dot-pot method in the permutations and combinations problem, and really any other major backtracking problem that we already solved on this channel, right? And ultimately, we can simply return solutions once we're actually done for every iteration of this for loop. And in fact, return solutions should be outside of the for loop, because we don't want it to be inside of the for loop, because that would basically return solutions for every iteration or every value within the range of n, which of course we don't want. And ultimately, outside of this code, we simply want to call or recursively call the backtracking function, not recursive, but just call it, with parameters 0 and empty sets for the column, anti-diagonal, and diagonals. And whatever this return type value is, the integer value of the number of solutions, is essentially what we want to return. Okay? So again, basically on lines 19 and 20, what we really do is, once all columns for the current row have basically been explored, the function basically returns the total number of solutions found for that row. And finally, on line 20, we'll call the backtrack function starting from row 0 and with empty sets for the columns, diagonals, and anti-diagonals arguments or parameters, and the result is the total number of valid solutions for the entire chessboard in this iteration or for loop up till n, which is our input, right? Basically the dimensions of the chessboard values, okay? And basically, to kind of overall explain what this code does is, we'll use backtracking to explore all the possible ways to place queens on the board row by row, right? And for each row, it tries placing a queen in each column, ensuring that no two queens attack each other. And if it places queens successfully in all rows, we'll increment the solution count, and after placing a queen in a column, the algorithm essentially recursively moves on to the next row. And of course, if it cannot place a queen in a valid position, we'll backtrack by removing the queen from that previous position and trying it to the next column, right? So if I were to submit this code right now, unless I spell something wrong or made any weird syntax errors here, this should be accepted. And as you can see, it's just about as efficient as you can get. A runtime, it says I have 50 milliseconds, but I only beat 50% of users. But if I were to submit this again, that number would probably skyrocket to like 90% of users, right? Yeah. So you really can't trust these beats slash percent of users on Leetcode, but you know it is what it is, right? So for the time and space complexity, the time complexity is going to be big O of n factorial, right, where n is the size of the board, and that's basically because there are n choices for the first row, n minus 1 choices for the second row, and so on and so forth, right? Hence the reason why our time complexity is going to be big O of n factorial. And for the space complexity, this is going to be big O of n, because we're essentially using sets to sort columns, diagonals, and anti-diagonals, each of which can hold at most n elements, or n is our integer parameter, or input rather, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.